My name's Andrew Layson. I'm Senior Principal Water Engineer at Jacobs Group. I've been in the water industry for over 40 years, always as a process engineer, applications engineer, design manager and so forth. The water industry is an interesting industry to be in. Water is used everywhere. Every industry uses water, which has meant that I've been able to work in a whole range of different water applications, breweries, drinking water plants, water reuse, seawater desalination, mining. I've been on manoeuvres with the Army, testing pilot equipment, whole range of stuff. And what's continuous through all of those industries is the importance of P&IDs. They are the fundamental document that everybody uses. They're the central source of information, the source of truth for a process designed for whatever process that you're talking about. Now, if you look at all of those different industries, you talk about military applications, microelectronics, mining, etc. They all have slightly different drivers, things that are important to them or not so important. But P&IDs are consistently the most important document. They will do them a little bit differently, they look a little bit different, perhaps the symbols are a little bit different, but some of the key principles about how you do a P&ID don't change. Some of those key things are, first of all, consistency. When you look at a set of P&IDs, you want those P&IDs to look consistent from the first drawing to the last. And in many projects you have over 100 P&IDs that you're working to. You want every P&ID to look exactly the same as far as the symbols that are used, the tagging, the way the flow runs across the page, the presentation of it. And what I often see when I look at P&IDs from people who are perhaps not as experienced in producing them is it doesn't look very professional because they're really inconsistent. I see different size symbols on one drawing to another. The tags don't flow. There's missing tags, missing information. The P&ID, as a process engineer, it's one of the key indicators of how professional you are in your job, how good you are at your job. And when someone looks at a P&ID, if it doesn't look very good, if it looks inconsistent, they're making a judgment about you as an engineer. So really important to think about the consistency of your P&ID, how it looks. Have you got the tagging consistent? Have you got the flows running sensibly? Is it easy to pick out the main process flow? Can you see where the main process flow is? Is it a nice thick line so you can follow it? Do the arrows follow correctly? Can you follow from one drawing to another? All of these things, which sound simple, but they're so important because people make a judgment about you and your work, and they help people use the information that you've produced. Clarity is another important element. Is it clear? I often see P&IDs that are just crowded with instrumentation. You look at it and you try to go, well, what is this I'm looking at? I can't understand what this drawing is telling me. You want to have clear, open space on your drawings. You want to be able to see things clearly. So that's a really important point. Just mentioned about people looking at a drawing and not being able to understand it. And I think this is probably a point on P&IDs that we sometimes forget. As engineers, we're focused on our design, and we do some great stuff as engineers. We do some really fantastic stuff. We're doing great things for the planet. We're doing great things for the environment and for communities and users. But I think sometimes we get so focused on the detail of what we're doing that we forget that the document that we're producing, the P&ID that we are producing, is going to be used by many, many people. And they need to be able to understand that information. Now, a lot of them are not process engineers. They're not chemical engineers. We're dealing with electrical engineers. We're dealing with structural engineers, civil engineers. They don't understand a process. Some of them barely know what a pump is. So when we have too much detail on a P&ID, if it's not aimed at our end user, the person that's going to use that information, then a lot of the good work that we have done in producing a really great detailed design gets lost. So it's important when we are preparing a P&ID to think about who's going to use this document, who's going to use it, who's going to look at it. Is it going to be operators? Plant operators will need it. Maintenance people will plan their maintenance based on the P&ID. It needs to be clear for them to see every piece of equipment that might be detailed, that they might have to maintain, that they may have to operate. The other thing I think is really important to think about in the changing world in which we live with AI and data management systems is that the P&ID is not just a capture of your design, but it's actually a great data source. And increasingly, we see P&IDs being married to databases of a lot of information that give you information about equipment size, the manufacturer, how often it needs to be maintained, the materials it's made of. And this is all happening in what we call smart P&IDs. So you have a P&ID that's drafted on a computer-aided device, CAD system, and inherent in that is a whole bunch of metadata, which is embedded behind the symbols. And then that can get exported out into a database, which then populates a whole bunch of things. The project I'm working on at the moment, we have smart P&IDs, and we're using that to automatically calculate cable sizes, to automatically do our switchboard designs, because we've got this captured information and metadata about each piece of equipment, which is used for subsequent calculations. So as process engineers, as chemical engineers, some of what we're doing with P&IDs is not just process engineering or chemical engineering, it feeds into electrical engineering, it feeds into mechanical engineering. All of these things, which it is the source. All these things we need to recognise as we put our P&IDs together, and remember that we're producing something that's not just a process engineering document, it's a document that's going to be used by everybody who works on the project, from the day that it starts construction to the day that it finishes and gets deconstructed. So P&ID really central, understanding that and thinking about all the uses of a P&ID, not just the initial design, what size pipes are we going to do, but all through the life cycle. It's really important. I think another element of P&IDs which is important to think about is its role in safety and design. I think I've been in the industry for a long time, and the way in which we have approached safety has changed and it's grown, it's improved over time. But I think unfortunately safety and design is something which is often done as a box ticking exercise at the end or towards the end of the design phase. And that's a great shame, because a P&ID is done right at the beginning of the project. It sets the tone for where the design is going. We can capture in that key safety and design elements which can reap a great benefit to everybody across the project. And it can be little things like, have you got enough isolation valves so that something can be safely isolated? Somebody can go into a vessel, a confined space, and know that they're going to be safe. Have we got enough valves to do that? Do we have enough isolation valves on pumps so that we can isolate a pump while the standby one is in operation and not have a hazard? Can we do things to reduce working at height? One of the greatest hazards we have in treatment plants today is still slips, trips and falls. Equipment mounted at height is a hazard. It also has an inherent cost to it. If we put level transmitters at the tops of tanks, we've got to have safe access to get there. That's a lot of steel that has to be designed. It's someone having to go up those stairs, disconnect the level transmitter, pull it out, take it back down again. People go up and down. All of that has an inherent hazard. If we can put our level transmitters at the bottom of a tank, we've eliminated the risk. We've taken that away. Now, that's not always possible for every material, but for a lot of cases it is. So we can think about that as process engineers, as chemical engineers, knowing what the fluids are, the materials are that we're containing in a storage tank, and thinking, well, okay, is there a smart way that we can monitor what's in this tank without creating a hazard? And the reality is that many times, yes, you can do that. And also, it reduces the cost of the project. It reduces the complexity of it. And from a sustainability point of view, that's great. We can actually do things in a P&ID which have a positive impact on the sustainability of our projects. And I think, unfortunately, sustainability, a little bit like safety and design, is often dealt with at the back end of the project. It's not really given the attention it should be given. As process engineers, as chemical engineers, we should be aiming higher, and we should be setting a standard for the rest of the engineering fraternity and saying, okay, we think about sustainability, we think about safety right up front, and we capture it in the key document for every other discipline we use, which is the P&IDs. So yeah, we're going to put our level transmitters at the bottom of the tanks because it's safer, it reduces the amount of materials that we're going to use, and it reduces the complexity of the design. Okay, so we've talked a little bit about what we want in a P&ID, what we're going to use a P&ID for. Might be worth taking a few moments to think about, well, what are some of the common errors that occur with P&IDs? And as I look at P&IDs across a range of years and different people with different levels of experience, I see quite a few common themes that come through. First one is lack of cohesion, where you look at two different drawings that are meant to be flowing from one drawing to the other, and there's no connection there. You just see that things don't match. Now, that lack of cohesion can be a number of things. It can be that the tags don't go from one diagram to another. They don't point to the correct drawing. It could be that we've got duplication of equipment on two drawings. So we have, say, a flow meter on the outlet of one drawing and another flow meter on the inlet of the next drawing. We've got two flow meters in parallel, which makes no sense. It just shows that there's been a lack of cohesion. We haven't tied these two drawings together. We haven't looked at them as a set. We've looked at them simply as one drawing and then another drawing, looked at them in isolation. And I think for process engineers, as part of what we do, we step back and we look at the system as a whole. Process engineers and chemical engineers, I think, are a little bit different to many other engineering disciplines in that we think in multiple dimensions. We're thinking about flow rate, time, we're talking about concentrations, reactions, and so forth. We see the big picture. We have to see it in the way our process works, but we also have to see the big picture in the way the drawings and the documentation tie together. So I think that's an important thing to remember. Another error I see is excess instrumentation. Instrumentation is really good, it's really important, and it's increasingly important in a world where our treatment plants are becoming more and more automated. The dream for a treatment process is that it's like the driverless train, that it can control itself, it can fine-tune itself, and it needs instrumentation to do that. But that doesn't mean that we have to put an instrument on every single thing, and in fact we can sometimes have too much instrumentation. You need to remember with instrumentation that it needs to be maintained, it needs to be calibrated, it needs to be looked after, it needs to be wired up. There's a cost in every instrument that you put in, not just in the capital cost, but in the operation and maintenance of that device. And sometimes we just don't need as much instrumentation as we put in. So it's a common thing when I see lots and lots of instrumentation, you ask, well, why does that all that instrumentation for? But sometimes we can dial it back. Another common error I see often is a lack of attention to safety in design. And I've already talked about the importance of safety in design. But as a fundamental principle, we need to be thinking about, can we isolate equipment safely? Can we keep operating the treatment system with one unit in standby? How do we do that safely? So thinking about safety in design, or lack of thinking about safety in design, is a common error that I see in a lot of drawings. When we look at a treatment facility and we design our P&ID and we put a certain instrumentation in, we often think to ourselves, well, this piece of information, this instrument is going to tell an operator some information and they will do something as a response. That assumption that somebody will take a positive corrective action in response to a measurement is vastly overestimated. So you cannot rely on an operator for anything. Now, that needs to be reflected in our P&IDs. We need to make sure that there is sufficient instrumentation and controls in there for a process to protect itself. And so these are a key thing that is overlooked often. People assume that an operator will do more than they will. So, what are some tips for producing a really good P&ID? First of all, it's important to have really good document control. Next thing to think about is the title block. The title block needs to be clear. It needs to display that information about drawing number and title and so forth. It needs to be clear what the drawing number is, what the revision is, who did the drawing and who prepared it, who approved it, so that there's some traceability. There should be a link to a legend sheet that tells people what the symbols mean. Next thing to think about is the overall layout of our P&ID. Generally, the flow should go from left to right. When a flow enters the drawing from the left-hand side, it's important to put the tag of what drawing it came from. Now, I often see people will say, this flow came from pump 64. My problem is I don't know which drawing pump 64 is on. What I need to know is what drawing is it on, and then I can go back and I can find pump 64. So really, where we have our connectors on the left-hand side, we want to say the drawing number and potentially the equipment that it came from, or at least the process fluid that's there. Similarly, on the right-hand side of the drawing where flow is leaving the drawing, we want the same thing. Which drawing are we going to? So I can go to that drawing, I can find where it connects. The next thing we need to think about is the main process line. It needs to be shown with a thicker line than all the other lines, so that straight away when I look at the drawing, I can see where the main process line is. It's important to make sure that you've got the arrows the right way round on those process lines. It's surprising how many times you see a line on a drawing and the arrow's going the wrong way, which is really confusing. Now, as a process person, you might go, oh yeah, I can just see that arrow's the wrong way. But you ask an electrical engineer or a mechanical engineer to understand that, and they won't. So it's important we get that kind of detail right. We have a lot of equipment that's shown on our P&IDs, and often we have duplicate trains. It's not necessary to show all the detail on every duplicate train. We can simplify our drawings by having maybe a special P&ID that details what's inside a piece of equipment, and then just on a master P&ID that shows the overall scheme, the parallel units, but just as a box. And there's an example here that you'll see on the screen. What you can see from this image is we have multiple process trains in parallel. They're just shown as a simple box. And then we have a separate drawing that shows the detail inside that box. And what this does is it helps communicate the overall design, because that first drawing you can see the overall flow through the whole system. You see the flow coming in from the left, you see it gets split across a bank of pieces of equipment, and then the flow comes together again and leaves. Now what's in those boxes? Let's look in detail at the next drawing, and you can see that information. You can imagine how crowded that first drawing would be if we tried to put all that information in every one of those boxes. It would be impossible. It would be illegible. Which leads me on to another point. Legibility of a drawing is really important. In this digital age, when we sit in an office and we work with our computers, we're used to seeing things on a screen. And we expect that everybody does that. But the reality is, people on site, when they're building something, they don't walk around with a computer. They walk around with a bunch of A3 drawings, and they're looking at those drawings and they're trying to work out what it is. They don't carry computers around. So that means that what we're looking at has to be clear on an A3 printout. So the size of the lettering is important. How crowded the drawing is important, because you can't read it if it's too small. Next thing to think about is labeling. It's important to label all of our equipment, give it a tag number so that people can refer to it. It's important that our pipes all have a label on them. And generally what people want to know is the diameter of the pipe as a minimum. Usually they'll want to see what material that pipeline is made of. There are some additional things you can put in there. Example of fluid code. What kind of fluid is it that's running through that pipe? That's kind of nice to have, not a mandatory, but certainly you want to see the diameter or the size of the pipe. You want to see the material. They're pretty key things. In every pipeline, you should be able to work that out. Another common error I see people making is confusion about instrument symbols. Now, we use a lot of instrumentation. I've already talked about the importance of instrumentation for our designs, and particularly for future-proofing them. So we do need a lot of instrumentation, but the way we display instrumentation, or we show it on a P&ID, needs to be consistent. People get pretty confused about it because there's a number of ways you can do the symbols, but the simplest elements to remember is, if it's a simple circle, it means that that instrument is in the field. It's on a piece of pipe, or it's connected to a piece of equipment. If there's a box around it, if it's sitting in a square, that means that it is mounted somewhere else. So it's not on the instrument. And they're the two key things to remember. If you see a square with a line through the center, that generally means it's on a control panel somewhere. A square with a diamond in it, often used for a PLC type indication. This is one where different industries do it slightly differently. Generally, there's a lot of stuff that's going on in a PLC, and it's detrimental to put too much of that detail trying to indicate what's happening inside the PLC on a P&ID. There's just so much happening, you'll never capture it. So it's not worth the effort. So to me, the simple thing is make sure you put the primary element, the thing that's in the field, that's got a circle, and then you show that there is an instrument that's on a panel mount. Different industries do things slightly differently. And I think this is one of the areas where you do see quite differences between different industries. Petrochemical people take a much more detailed view to the way they display instrumentation and controls on a P&ID versus, say, people in the mining sector or the water industry or some of the other industries. So this is one where context of the industry you're working at makes a difference. There's nothing wrong with that as long as you're consistent through your whole drawing set. But from a design project point of view, what you're doing at university, you probably don't need that level of complexity. Keep it to the more simple symbols. So we talked about a lot of stuff. Let's wrap this up with a few key things. What are P&IDs there for? They're to capture our design, but equally as important, they are to communicate our design to others. They are the central source of information. They're where the data gets embedded, which is going to be used by every other person who's working on the project. So let's not think about P&IDs as a document that we own and that's ours. Think of it as a document that we prepare that is shared and relied upon by everybody in the project. The other thing that a P&ID does is it communicates to the rest of your team your competence. Rightly or wrongly, people will look at a P&ID and they will make a judgment about the person that prepared it or the team that prepared that. A P&ID is really a demonstration of your competence and your professionalism. So it's worth spending the time to get it right. It's worth caring about the little things. Does this drawing look right? Is it easy to understand? Is it consistent? Does everything flow from left to right? Is everything labelled? All those little things, you add up all those little things and they're a big thing. They're a big thing that reflects on you as a professional. So good luck with your P&IDs. I look forward to seeing many of you people working in industry producing fantastic P&IDs.